And we are back on to lecture 3, and we're going to talk about some of the probability distributions that you may encounter. And we're going to also go through how are we going to plot some of these distributions as well in R. So we've talked about ways that we can um, basically work with histograms to represent data. And data comes in various forms. There are various distributions that you can encounter. So one of those distributions is a random distribution or a uniform distribution. So this would be a distribution you can expect to see, for example, if you are rolling die, right? So if this was a 10-sided die, these would be essentially the counts that you may expect from a random distribution or a truly random or stochastic or a Markov process. So this is typically what you can observe. So a lot of times when you're in a simulation system, there are some, but very few experimental systems that show this. So that is something that we have to think about and effectively consider when we're looking at it. You can also have an exponential, or sometimes called a negative exponential distribution. So you can see this distribution. It's again high probability or high counts at the beginning, and it slowly decays off. And that rate of decay depends obviously on the scenario. Uh, this distribution actually it captures really well like the time it takes a radioactive particle to decay, or even for some financial models, the time until default on payment to debt hold in some financial models. So uh, exponential distribution you can kind of see here, and this is one of the key kind of parameters here is that uh, the exponential distribution can be fit by a function, and typically there are some parameters here that are fitting functions, obviously to fit, that can be changed depending on the experimental system. And you can see usually it can be represented as the basically the population mean or the standard deviation. Here is a unique one because actually population mean and standard deviation are represented by the same variable, which is very unique. You could have a Poisson distribution, and we can kind of see the Poisson distribution. It looks a little bit Gaussian, but you kind of have a little bit more of a right shift slant, so to speak, a longer right-sided tail. So it's very good to look at the number of meteorites that hit Earth, as well as student exam score distributions. So you can see essentially this distribution below. We can do a binomial distribution. So a binomial distribution looks, again, quite Gaussian. This is not, binomial shouldn't be confused with bimodal. We could have a log normal distribution. So you kind of see, again, a longer, effectively a tail that is observed. So there's lots of phenomenon that actually are described well by the log normal distribution. So the length of chess games. So again, it kind of makes sense, right? Like this, you have longer tails where some chess games can be extremely long. Size of living tissues, hydrology phenomenon, and we can see some of the parameters now. Again, this is our population mean. This is our variance or our population standard distribution. You can have a beta distribution. So we can see a beta distribution here. And again, those are described by these kind of two parameters, alpha and beta, as the name implies, to kind of see how the difference there. So these are very good for allele frequencies, project management models. Again, you have to see what is the appropriate distribution that you expect from your data, but also what is your data, and then what is the best distribution to fit. And we'll be getting into that in lecture 10 in terms of fitting and how do we determine best fit and all those other great things. You can have a gamma distribution as well. So somewhat similar, looks like a little bit to the exponential or decayed, but you can kind of see some of the variables here. But it's very, very good for age distribution for cancer incidence, as well as the size of insurance claims, rainfall, and again, you can kind of see high incidence of cancer, and then it obviously decays for certain ages. The Weibull distribution is it's one near and dear to my heart from materials. That is really, really well at describing effectively fatigue measurements. So I am it's that one's very near and dear to my heart. Now, before we get into the Gaussian, which is probably the most famous and the most likely scenario, let's see, the most likely scenario, or the most likely distribution that you will encounter, let's get into R. So I'm going to install these packages and then read in tidyverse and ggplot2. And you can see here, I am going to create my own data set. So I'm just going to create and pull from a random uniform distribution. And I'm going to create that data. And then I'm going to do data frame so we can plot it. And then if you look at here, all I'm doing in the data frame is I'm taking in this, if I just look at this U distribution, it's just numbers, 5,000 numbers from 0 to 100. But I could frame it and give it a column header. And that's going to be helpful because when we plot, we're going to use our ggplot. You're going to read in the data, which is this US data. And then on our axis, we're going to put on the x-axis our basically that column, that uni column. And then we're going to add our geom histogram and then themes. And it's our measure and count. And so you can see our beautiful uniform. And you can change the bin width. So I could change the bin width to be 1. I can change the bin width to be 50. That's not going to be. So again, depending on the bin width, you can make your distribution appear a little bit dissimilar or a little bit different. But again, this is a pretty typical random distribution. We can change the values here. So I could just change the max to be 10 and replot everything. So now the bin width of 5 is too small, so we probably want a bin width of 1 at least, or even like probably 0.5. So again, you could change some of those parameters. The uniform, there's not much to play around with. But the exponential, here we can again start to plot, and we can see these exponential values here. So the exponential, you can change some of the parameters. So you can look in the help like our exponential, or you can kind of start to, but you can kind of vary essentially the values here. So you read in, for example, for our exponential, you're gonna the number and then the rate. So the rate here is essentially that that tail. So we can set that value to be 1. So let's actually replot it. If we want the rate to be faster, it could be 5, for example, and we can see what happens. So see, if it decays faster, now we're probably going to have to do a smaller bin width, so like maybe 0.05. And again, you have to kind of see again how fast it's decaying. If it's a decay rate of 0.5, I mean now this is too much. So again, bin width maybe of 0.1 is better, or you can do probably even 0.5. So you can change essentially again if you're we're creating the data here. Typically, you're going to read and see how it looks. But you can see here we have a Poisson ratio, kind of a similar thing, showing essentially this decay here. So if we change it to, for example, 5.6, let's see what we see. You can kind of see some differences in the values changing, right? So if I change from 4.5, we'll probably see that the x-axis decrease in terms of the range that we see. Or you see kind of that little longer tail eventually emerging here. So if we go to 4, you can even you see, right? Like you see essentially that decay and moving over. But anyways, you can have a binomial distribution, and again, you see 2 parameters, right? So the number of data points, and then also the 2 parameters that we're going to effectively be varying here. So here, this looks, very pretty Gaussian. You can kind of see here. Then you'd have to change essentially that bin width. So here, if it's 1, what do we do? Let's see. So you can kind of see the differences that are effectively occurring here. We get much tighter, right, as we get those values. Log normal, so you can see the mean of the log, standard deviation of the log, and we can go through, and you can see, again, some of the variables, essentially, that you can look through, the beta distribution as well. So, again, these are all commands, the gamma distribution, the Weibull distribution. These are all effectively ways that we can plot and look at histograms and visualize data, except here we're actually creating that data set. But you can do the same thing reading in. So, we will see you all in the next video when we look at Gaussians. See you then. Thanks. Bye.